So remember that last week we discussed the uniqueness theorem, and so one application of the unique theorem is the Faraday's cage. So we spent quite a few times talking about the Faraday's cage, and so there is a conductor outside E equals 0, and but for a conductor, the V here is a constant. And if there are no charge inside, then what's inside is simply a Laplace equation that's with a boundary condition of a V being constant on the edge, right? And for this problem, it's a trivial solution that V is constant, not only on the edge but also inside everywhere. Then if you calculate the E field, the E field will also be 0. And so from the uniqueness theorem, it's a one-line derivation to get that inside the cage, the E field should be always 0, no matter what's the electric field outside the conductor. Now, so in this lecture, we try to apply this uniqueness theorem to other methods of solving the problem. So the first trick that I want to introduce is the method of image. So the method of image is asking a question of a point charge. Say here is floating at the here charge Q, and there is also a grounded conductor at the xy plane. So it's this shaded regime. Now the question is, what is the electric field above this conductor? So you might think that why not use the superposition principle and separate the problem into two steps. One is the problem of a conductor, another is the problem of a point charge. Well, the answer is that this separation is not possible because if you can see that if there is a point charge here, then this charge will attract the negative charge near this center. So in the middle of this, there will be a negative charge accumulating, and there will be less and less negative charge as you go far away from the origin. So there will be a complicated surface charge distribution on top of this surface. If you want to use the superposition principle, you need to determine the surface charge distribution first. And that is not a trivial thing to do. So instead, what we can do here is we forget about this conductor for a moment, and let's take a look at a completely different problem, and say the problem on the right hand side. So here we look at a simple problem of 2 point charges. One is the original one sitting at a d of distance above the origin. Another is an image charge that's sitting at the opposite direction of d, and is sitting at negative q, with charge negative q. Here, if you go back to the original place, you can see that this image charge is actually out of the area that we are of interest. We are only interested in the E field above this plane, but we place this image charge somewhere below that plane. And let's see if we can actually solve this problem. This problem is really being solved in the second lecture for a 1D case, right? We simply need to generalize the result to 3D. So let me simply write down the result. So for a single point charge, the potential V is simply 1 over curly R, and so it's 1 over 4 pi epsilon naught 1 over square root of x squared plus y squared plus z minus and here this is the here this is the contribution for the first point top charge, and now the contribution from the bottom negative charge is simply the negative of square root of x squared plus y squared plus here this curly R is with respect to a slightly different coordinate, and this is the total potential for the 2-point charge. And now if we take a look at this potential is actually special in the sense that say one trivial limit is at v equals infinite. When r goes to infinity, these two cancels and the result is 0. And if you look at when d go to 0, you can actually see that here this when z go to 0, this term actually is exactly the same as this term. So actually the two denominator become the same. Minus d squared equals plus d squared. And this means that on the entire xy plane, as long as z is 0, the final result should be 0. And if you look at the problem that we are trying to solve before, the problem we are trying to solve is exactly has the v equals 0 at the xy plane. So you see that somehow magically, if we position a negative q charge below, these two together will generate a equal potential surface exactly at xy plane, and this will automatically satisfy the boundary condition on the left. And even though we somehow guess an answer, and this answer actually should be the solution to the question on the left. At least it's one of the solutions, right? Because this solution is a solution for the problem on the right, but it also accidentally turned out to be a solution for the problem on the left, because on the plane that's xy plane, the v accidentally becomes 0, and for all the E field above, it should be automatically satisfying the Poisson's equation, because on the plane above we also have a single point charge. And now if we use the uniqueness theorem, then this means that because this is accidentally one of the solutions that we find, and this has to be the unique solution, there are no other solutions. So this means if you are able to guess a solution, then you are done with your work, so that in your homeworks you can say that, well, somehow magically I think the potential should be looking like this, and if you check the boundary condition and say, well, the boundary condition works, and if you plug in the Poisson equation or the Laplace equation, you find that it satisfies everywhere, then this has to be the solution. So there cannot be another solution. And so this is the magic of the uniqueness theorem. And we use that here in the method of image to guess a solution first. And then if we are able to guess a solution, then this solution has to be the solution to the answer. Well, this is the logic, but in reality, it might not be easy to guess, right? So I'll talk about later how we can guess, but let's now to check if it's really the case. So if we look at the E field of the two cases, the E field is simply negative the gradient of the scalar potential, and you can actually check that the E field look like something like here on the left. So here I try to plot the two charges, one on the right and one on the left, and now you can see that here in the right in the middle, that's the plane of the conductor, and this is the xy equals 0 plane, and now the E field simply go from the if you use the language of field lines, then the field line simply goes from the positive charge here to the negative charge, and magically at exactly z equals 0, this field line goes perpendicular to this plane, so that here this is always perpendicular to this plane, and here this perpendicular plane can be if you connect everything perpendicularly to the field lines, saying that one possibility is this potential. So this is the equipotential, and this is where V should be a constant. And similarly, you can see that the equipotential can also be this circle, which is always perpendicular to this field line, electric field lines. And say that if you are asked somehow to ask the question of calculating the conductor and of this very strange shape, and if somehow magically you find that if you position a point charge here, and the field always go perpendicular to this conductor, then this is the solution that we are looking for. So say in another words, if you find the E field of this two image charge, and if you simply look for any equipotential curves and associate all these curves, say that associate this curve with the surface of a conductor, then this on top of this surface of this conductor, the potential should be a constant, and that should simply be the solution to your question that you're looking for. And this conductor, you see that not necessarily need to be a plane, can be a very strange shape. As long as you can find this potential, then it works. The trick is like it's not easy to find this kind of image problem first. So sometimes people actually do the problem in the reverse way. So they first solve for this problem, and they locating this equipotential lines, and then claim that now if we replace that with a conductor, then that should be the solution of the conductor, instead of directly working from the right to the left. Now let's really try to make sure the two are the same solutions. Now if we try to calculate the surface charge density, remember that the in the lecture 3, I think we discussed like what suppose there is a conductor, and then the E field should be always be perpendicular to this surface, and there is a relationship between this E field and this surface charge density, and this E field should be should be proportional to this surface charge density, and the E is also partial V partial n, and so this means that now if we take the partial V partial n, it simply gives us the surface charge density. So now this surface charge, now this normal direction is, in our problem is the z direction. So here this charge is simply partial v partial z at z equals 0. Now if we plug in this expression for the v that we obtained earlier, and take a partial derivative at z equals 0, we get and this thing should be evaluated at z equals 0. And now if we simplify this expression, this is actually something simple. Now if we look at this expression now, we see that remember that this is the surface charge density, and you can see as x goes to 0 and the y goes to 0, this function takes extreme value, and it's the most negative because there is a minus sign here, and that is somehow correct according to our intuition, right? We think that when there is a point charge here and there is a conductor below, then this point charge will attract most negative charge right below this charge itself, and as you go slightly away from this point charge, then what you see is that the charge density decays, and how it decays is according to this expression. And now let's try to see what's the total induced charge.
If I set c equals to 0, then the denominator will cancel out. I have plus 2q
Oh,
minus 2.
I think I may, let me see, I may have missed a negative sign here. Let's check. So partial v partial z, yeah, I think I made so I should take a partial derivative of this expression, and so this is minus 1/2 and z minus d. This is minus 1/2 z plus d. So there should be two minus signs, and I may have missed one. So if there is a additional minus sign, then the z on the top cancels, and what's left over is the d. So Right? Let me see. Okay, yeah. Okay, now let's try to see what's the total charge if we integrate this surface density over the entire surface A. And now if we can actually redefine the x squared plus y squared as s squared, and this is the polar coordinate, and we simply integrate the sigma as a function of s and theta. Let's write out this first. And here on the right should be s d theta ds. Now in the angular integral, that simply gives you 2 pi, which cancels this 2 pi. And on the s integral, the s ds can be replaced by s squared, and then ds squared and half. And then it can help you do the integral, which is simply and that is now at s equals to infinity, this value is 0, and at s equals 0, this is simply qd times 1 over d squared and half and to the power of 1/2, which is negative q. So now you can see that actually the charge that the total induced charge on the surface of this plane is exactly minus q. So you can think that you try to do a Gauss integral that's enclosing the total surface. Then what's enclosed right below should be negative q, and that is actually the charge of this image charge. So without this conductor, if you do the same Gaussian surface integral, that also gives you negative q. So this might not be so this might be the reason that people actually try to use the idea of the image charge. This total charge, real charge on the surface is actually exactly identical to this imaginary charge sitting at this point right below